Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you are shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeters is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. Now we will discuss the second part of module 3, which is combinational circuit design, which is dealing about the introduction about the combinational circuit design and the different circuit families involved in it. So basically we have seen that digital logic is divided into combinational and sequential circuits. So combinational circuits are those whose outputs depend only on the present inputs, while sequential circuits have memory. So it is followed one after the other, therefore they have memory. Generally the building blocks of combinational circuits are simple logic gates, whereas for sequential circuits it is resistors and latches. So now here we will learn techniques to optimize the combinational circuits in order to reduce the delay and the energy or the power consumption. So the majority of the circuits use static CMOS, which is under combinational logic circuits, for the reason that it is robust, fast, energy efficient, and it is easy to design. But however, certain circuits have particularly stringent speed, power or density restrictions that force another solution. So CMOS is very much dominantly used, but still there are some flaws. So the flaws are, it is with respect to the speed and power or density. Therefore, we have to go for an alternate solution, and that is called as circuit families. So what exactly is circuit families? The basic concept of the CMOS retains with modified changes. So CMOS concept is retained, and in addition to that we have few more changes in the circuit, and we call them as ratioed circuits or dynamic circuits or pass transistor circuits. Like this we have still many more: pseudo NMOS logic, clock logic, so many things, but here we focus our concentration towards ratioed logic, dynamic circuits and pass transistor circuits. So NMOS transistors provide more current than PMOS for the same size and capacitance. So NMOS circuits are preferred. So since the majority charge carriers in NMOS are the electrons, therefore they are comparatively faster than the PMOS in spite of being of the same size. Therefore, the logical effort is proportional to C by I term, because it is determined by the input capacitance of the gate that can deliver a specified output current. But the drawback of static CMOS is that it requires both NMOS and PMOS on each input. So every time we have to consider NMOS and PMOS, and one at a time is working. But when there is a falling output transition, the PMOS transistors add significant capacitance without helping the pull down current. So PMOS transistors during fall output transition, that is from 1 to 0, PMOS transistors have their capacitances and therefore static CMOS has a relatively large logical effort. So though the PMOS transistors are not considered in the falling edge, the capacitances are considered, and therefore they are having a capacitance effect, and therefore CMOS has a relatively large logic effort. So how to overcome this? The alternative mechanism is to pull the output high. Therefore, monitoring inputs and outputs inevitably loads the nodes. So clocked circuits are often used. Therefore, to overcome this, clocked circuits are used. And one more thing, drawback of the static CMOS is that all node voltages must transition between 0 and VDD. So the transition in CMOS is the minimum is from 0 and the maximum is from VDD. Maximum is VDD. But so many families don't completely fall into 0 volts and complete VDD volts because of the threshold voltage effects. So the voltage swings are not from 0 to VDD, it can be from zero point 0.2 volts to, if it is 5 volts, it will be 4.8 volts. And that is circuit families use reduced logic, reduced voltage swings, and to improve propagation delays. So this is also one drawback of CMOS. Therefore, this can be considered against the delay, and therefore the amplifying is helpful, and therefore we are able to reduce the tolerating costs of the swings. Next we have silicon on insulator. This is also one technique which eliminates the complete substrate structure. On an insulator we are trying to build up a circuit. So the advantage of this kind of technique is to achieve lower parasitic capacitance and better subthreshold slopes. Therefore, lower power and higher speed can be achieved when you are going for SOI techniques. Now we look into the circuit families. So far we have discussed few of the flaws involved in static CMOS. Static CMOS circuits with complementary NMOS pull down and PMOS pull up networks are used for majority of logic gates. So normally in CMOS, static CMOS, we have pull up network as the PMOS and pull down network as the NMOS. These circuits have good noise margins. Yes, we have seen so far. They are fast, they consume less power, they are insensitive to device variations, they are easy to design, and they are supported by CAD tools, and therefore very predominantly they are used in standard cell libraries. Because of all these advantages, it is predominantly used. But most design teams now use static CMOS exclusively for combinational logic. So for combinational logic especially this is used. Therefore, this section what we are going to now understand is with a number of techniques for optimizing static CMOS circuits. How to optimize the static CMOS circuits is what is the focus all about. So the performance or area constraints occasionally dictate the need for other circuit families. So based on the performance and for the area requirement, we go for a optimized circuit with respective to CMOS, and of which the most important one is the dynamic circuit. However, dynamic circuit will be differed. We'll talk about this later on, but right now we'll consider the ratioed circuits, which are simpler and they offer a helpful transition between static and dynamic. So we'll understand first the ratioed circuit, and at the end later on we also consider the pass transistors, which we have already been introduced to the pass transistor in the first module, and they had their prominent place in the early 90s, and even now in most of the applications they are used. So pass transistor and transmission gate are right now used in fast switching actions multiplexers. So this is the preamble for the circuit families. Now we still focus on static CMOS. So all the while designers are accustomed to AND and OR functions, and now they should think in terms of NAND and NOR. So in manual circuit design this is possible, and it is done through bubble pushing. So what exactly is bubble pushing we will see in the forthcoming slides. And we also have compound gates. These compound gates are particularly useful to perform complex functions with relatively low logic efforts. So along with this we also have to understand what is a compound gate. These are useful to perform complex functions and they consider very low logical efforts. Similarly, when it is rising or falling edge, the gate can be optimized to favor that edge. So we have focused on, now what exactly we do is we focus on building gates with equal rising and falling delays, and however use smaller PMOS transistors which can reduce power, area and delay. Now we will understand the concept of bubble pushing. Bubble pushing is using the bubble. So CMOS stages are inherently inverting. Therefore, they are meant for inversion because you have two gates the two devices complementary, and and OR functions must be built from NAND and NOR gates. So if you have a NAND gate, if you split this using the De Morgan's theorem, you get it as A bar plus B bar. Similarly, if you have a NOR gate, A plus B whole bar, you get it as A bar dot B bar. So these relationships are illustrated graphically. So this is a NAND gate, and NAND gate will be got here as A bar. So one input A is inverted before it is fetched into the gate. So the inputs are A bar and B bar, and this gives you the output. Similarly, the NAND gate, NOR gate is also having a bubble prior to the gate itself, that is at the input side. This gives you A bar and B bar, and this is your AND gate. So these relationships are illustrated. Therefore, a NAND gate is equivalent to an OR of inverted inputs. A NOR gate is equivalent to an AND of inverted inputs. Therefore, the relationship applies to gates with more inputs. So switching between these representations is easy to do on a whiteboard and is often called as bubble pushing. So this procedure of converting one gate to another gate is done with the help of bubble pushing, and this is the concept of bubble pushing. Next we have compound gates. So you have static CMOS also efficiently handles compound gates, computing various inverting combinations of AND and OR functions in a single stage. So we have a function f is equal to AB plus CD, which can be combined as this is your OR gate, sorry, this is your AND gate, this is your AND gate, and the combination of these two gives your OR gate. So computed with an AND or invert 22 to 2 gate, and it is an inverter as shown in figure. So what is it you get? You have one AND gate which is AB, you have another AND gate which is CD, and the whole of these two inputs AB plus CD bar is got at the output of this. To overcome the complement, you have to again bubble push in front of the inverter, and you get your final output F, which is equal to AB plus CD. So you had this NOR representation as bar, the bar is removed, and finally you get F is equal to AB plus CD. Now we look into the topic which is called as ratioed circuits. So CMOS, what is there, is modified and it is called as ratioed circuits. So what is a ratioed circuit? Ratioed circuits depend on the proper size or resistance of devices for correct operation. So in a ratioed circuit, you should have the proper size of the resistances of the device. So that in turn is completely dependent on the W parameter. So conceptually, the ratioed gate consists of NMOS pull down network and pull up device called as a static load. So whatever the device is there in the pull up region, it is considered a static load, and whatever is there in the pull down region will be your NMOS. So when the pull down network is off, the static load pulls the output to 1. It is completely dependent on VDD, and therefore the output would be 1. Entire VDD would flow at the output, and therefore it is logic 1. However, when the pull down network turns on, it fights the static load. So when it is when the pull down network is on, then there is a path for the load and it tries to go to the lower potential. So how can we have a topic discussion on this particular static load? So the static load must be weak enough that the output pulls down to an acceptable 0. That means since it is to the lower potential, it is pulled to 0. Therefore, there is a ratio constraint between the static load and pull down network. So one at a time static load is equal to 1, and at one time it is equal to the pull down network 0. So stronger static loads produce faster rising outputs, but increase VOL degrade the noise margin. Of course, we have the static output which is equal to VDD, but when you have VOL, that is the output low, it degrades the noise margin, and therefore it requires more power when the output is 0. So this is one disadvantage when you are using a static load. So unlike complementary circuits, the ratio must be chosen so that the circuit operates correctly despite any variations from the nominal component values that may occur. Therefore, this is the problem if the ratios are not properly selected. Therefore, in order to see to it that the device works properly, the ratios should be properly selected, which gives you the proper answer. or the proper voltage swing. The next topic is called as pseudo NMOS. So this is the pseudo NMOS representation. So what exactly is pseudo NMOS? You have one PMOS and one NMOS. And to the pull down NMOS, the input is given, and in the pull up region you have the PMOS, but the gate is grounded. So this is your pseudo NMOS inverter, where you give the input to the NMOS device. So neither high value resistors nor depletion mode transistors are readily available as static loads in most CMOS. So this is the skeletal structure of a pseudo NMOS inverter. So you have the PMOS and the gate of it is grounded. Next you have cascode voltage switch logic. So cascode voltage switch logic is given as CVSL3. It is a ratioed circuit which has static power without the static power consumption. It consumes no static power. Therefore, it uses both true and complementary input gates and computes both true and complementary outputs using a pair of NMOS pull-down networks as shown in the figure. Next slide will show you the diagram. So the pull-down network F implements the logic function as a static CMOS gate, while F uses inverter feeding inputs. So we will first look into the diagram. So this is the cascode structure, where you have crisscross junctions. One input feeds the other output. This is how it shows, and this is your cascode structure. So figure B shows a cascode AND and NAND gate. Normally you have the combination of AND and NAND, and that is the beauty of cascode structure. Similarly, it shows 4 input XOR gate. So the pull down networks share A and A transistors to reduce the transistor count by 1. CVSL has a potential speed advantage because all of the logic is performed with NMOS transistors, thus reducing the input capacitance. It fights the pull down network, so a large PMOS transistor will slow the falling transition. A small PMOS transistor is slow at pulling the complementary output high. Therefore, the CVSL gate requires both the low and high going transitions, adding more delay. Contention current during the switching period also increases power consumption. Pseudo NMOS worked well with wide NOR structures, but the disadvantage of CVSL is it requires complement. A slow tall NAND structure. If you have to work with AND, you also have to have a NAND structure. So that is considered as a drawback or a limitation of CVSL. Therefore, CVSL is poorly suited to general NAND and NOR logic. So standalone it doesn't work. It is always working with a combination. Even for symmetric circuits like XORs, it tends to be slower than static CMOS as well as more power hungry. So as a whole, CMOS compared with CMOS and CVSL, static CMOS takes an upper hand. However, the ideas behind CVSL helps us to understand dual rail domino and complementary pass transistor logic. However, if you are aware of what exactly is CVSL, the next topics will be easy to understand, and that is how it helps. So now we have the pass transistor circuits, which has already been discussed. So in pass transistor circuits, inputs are applied to the source and drain. Normally gate would be the input terminal, but here in pass transistor the inputs are given to the source or the drain, and subsequently the output is also collected either at the source or the drain. So these circuits build switches either using NMOS pass transistor or parallel pairs. Now if you use NMOS and PMOS in parallel, it gives rise to transmission gate. If it is used alone as NMOS or PMOS, it gives as pass transistor. Many authors have claimed that area, speed, power is improved in pass transistor compared to CMOS logic. So people have claimed, and the research has been done with respective to this. Therefore, in specialized circumstances, this can be true. For example, pass transistor is essential to design efficient 6 transistor static RAM cell. Because it consumes less space, and it has good efficiency in terms of speed, and it consumes less power. It can be used in designing a 6 transistor static RAM. Full adders and other circuits are also used using pass transistor concept, which is efficient, and an independent evaluation finds that for more general purpose logic, static CMOS is superior. So when you see as an independent evaluation, static CMOS is still better in all aspects in terms of speed, power and area.